What if we slowly remove the atmosphere? More specifically, what if we remove the atmosphere layer by layer? The atmosphere is made up of several layers, and each one plays a critical role in protecting life on our planet. In this video, we'll explore what would happen if each layer of the atmosphere vanished one by one, starting from the outermost layer and working our way down to the air we breathe every day. First off is the exosphere. The exosphere is the outermost layer of Earth's atmosphere. We'll define it at about 600 kilometers above the Earth's surface and gradually fading off into space. In this layer, air particles are so spread out that collisions between them are extremely rare. If the exosphere were to disappear, the effects on Earth would be relatively minor. Satellites in the region would no longer experience atmospheric drag, meaning they could stay in orbit longer without needing rocket boosters to maintain their orbit. Because it contains very little air, the overall air pressure on Earth would remain nearly unchanged, with the exosphere containing approximately 0.1% of the total atmospheric composition.
Okay, the exosphere wasn't so interesting, but what about when we remove the thermosphere next? It's the next highest layer of the atmosphere and contains mostly oxygen, atomic nitrogen, and helium. A lot of X-ray and solar radiation is absorbed in this layer, so you can imagine what happens once we remove it. First, the high-frequency intense radiation from the cosmos and sun will damage any low satellites with incredibly tiny computers with tiny components, as the small particles can easily disrupt their function, and radiation will penetrate further into the atmosphere. And while this will increase the UV that reaches the surface of the Earth, we will still be mostly protected by the lower atmospheric layers. The thermosphere was also responsible for keeping the radiation energy on Earth, as it absorbed the sun's radiation to heat up the gas to extremely high temperatures. You would think that without it, the Earth would heat up to ridiculously high temperatures, but actually, the radiation ends up getting absorbed by the lower layers of the atmosphere. Since there are slightly fewer particles in the overall atmosphere, the Earth actually cools a little bit. We can estimate the change in the temperature by first finding the molar mass of air if we treat it as a single molecule or atom. With this, we can find out how many moles of air are in the atmosphere, and because the thermosphere makes up only 0.002% of the atmosphere's total mass, find out how many moles are in the thermosphere. Then, using the equation U is equal to 3/2 nRT, and knowing that the average temperature of the thermosphere is around 1000 Kelvin, we can estimate the thermal content in the thermosphere to be 4.44 times 10 to the 19th joules. Most of this energy is in the thermosphere comes from the absorption of X-rays and UV rays from the sun and space. We can then find the change in temperature using Q is equal to mc delta T. NASA estimates the specific heat of air, treating it as a single substance, to be 715 joules per kilogram, so we'll use that. Solving for the change in temperature, we get 0.012, which is essentially nothing. And 3, the ionosphere is a sublayer of the thermosphere, and because of that, we are going to consider removing the ionosphere as a byproduct of removing the thermosphere as well. The ionosphere is created as a result of the sun's intense radiation knocking off electrons from neutral gas atoms, and is able to refract radio waves instead of being absorbed by other atmospheric particles. With the ionosphere removed as well, long-distance radio communication will fail as radio waves would continue out into space. We would also lose most of our northern and southern lights, as well as another phenomenon called airglow. Airglow is the result of a process called photoionization, which can be called a distant cousin of the photoelectric effect, and occurs when atoms are excited by sunlight. To rid the additional energy, a photon is emitted, resulting in colorful patterns high in the atmosphere. And similar to the exosphere, there is little atmospheric mass in the thermosphere, so the atmospheric pressure would barely change at all. Now what about the mesosphere? The mesosphere is, or was, the middle layer of the atmosphere, and is the point where air is dense enough to disintegrate most of the meteors that fly into Earth. This is because the speed at which the meteor enters creates friction with the gas molecules in the mesosphere to burn up. Now, if we were to remove it, suddenly many more meteors and fireballs will hit the surface of Earth. However, just like the previous layers, the mesosphere does not contain that much mass itself compared to the lower layers, meaning that the atmospheric pressure once again barely changes.
Now, let's remove the stratosphere. The most immediate problem is that the ozone layer disappears with it. Without ozone absorbing ultraviolet radiation, deadly UV light reaches the surface, and weather patterns become majorly disrupted as there is no more ozone to absorb the energy. Some photons, most notably UVC photons, carry enough energy to break chemical bonds in biological molecules and damage DNA directly because they can have wavelengths as low as 100 nanometers. In other words, going outside without protection would become less of a health risk and more of a speedrun challenge. Atmospheric pressure would drop as well, since the stratosphere contains roughly 15 to 20% of the atmosphere's mass. However, this wouldn't be instantly fatal. The change in mass will only make it so that sea level pressure would become similar to what we experience on a high mountain. Breathing would be more difficult, but there would still be enough oxygen for most people to survive. Humanity is not wiped out yet, but life would become much harsher, even before we start removing the next atmospheric layer. Now we remove the troposphere, the final layer. At this point, there is no atmosphere left. The air pressure drops to near vacuum conditions, meaning the planet stops behaving like a planet and more like space. Without atmospheric pressure, liquid water becomes unstable. It will rapidly evaporate and potentially even sublimate. Oceans don't freeze first or boil neatly, they just disappear into vapor. Sound also stops completely. With no air molecules to carry vibrations, the world becomes silent. Now thermally, things become extreme. Without an atmosphere to store and redistribute heat, the temperature starts to swing wildly. Greenhouse gases are gone too, so there's nothing trapping heat at all. Over time, the surface would settle to a temperature we can calculate using the Earth energy balance equation, which is 1 minus the Earth's albedo or reflectivity, which is about 0.30, times the solar constant, which is about 1,361 watts per square meter, over 4, equaling the Stefan-Boltzmann constant, which is about 5.67 times 10 to the negative 8 watts per square meter times Kelvin to the fourth, times the equilibrium temperature to the fourth. When shifting around the variables, we can find that the equilibrium temperature is equal to the fourth root of 1 minus the Earth's reflectivity times the solar constant over 4 times the Stefan-Boltzmann constant. When plugging in the variables, this equals roughly 255.26 Kelvin, which is equivalent to negative 17.74 degrees Celsius.
So, it turns out that we need the atmosphere for a few things we use in life, like water, air, and of course seeing our beautiful northern lights. So what if we slowly remove the atmosphere? Well, nothing that you would like would happen.